Welcome back to the Cosmic Atlas, where we explore the most extreme corners of our universe and ask the questions that keep astronomers awake at night. I'm your host, and today we're embarking on one of the most terrifying journeys imaginably not to a black hole, not to a neutron star, but to something equally deadly and far more violent, a Wolf-Rayet star. Today, we're asking, what if you fell into WR 124? This isn't just any star. This is a cosmic monster in its death throes, a stellar titan that's literally tearing itself apart. It's one of the hottest, most luminous, and most violent objects in our galaxy. And if you somehow found yourself falling toward it, well, let's just say it would be the shortest and most spectacular and you could possibly imagine. Before we descend into this stellar inferno, let's understand what makes WR 124 so incredibly dangerous. Buckle up, cosmic explorers, this is going to be intense. Located approximately 15,000 light-years away from Earth in the constellation Sagitta, WR 124 is not your typical star. In fact, calling it typical would be like calling a volcanic eruption a mild inconvenience. This stellar behemoth is what astronomers classify as a Wolf-Rayet star, one of the rarest and most extreme types of stars in the universe. To truly appreciate the scale of WR 124, let's put it in perspective. Our Sun, which we think of as pretty impressive, has a mass of, well, one solar mass, by definition. WR 1224. It currently weighs in at approximately 30 times the mass of our Sun. But here's where it gets interesting. This wasn't always its mass, you see. WR 124 has already shed at least 10 solar masses worth of material into space. That's right, this star has literally thrown away material equivalent to 10 entire suns. It's been on a crash diet. And the weight loss program is killing it quite literally. Now, let's talk about temperature. Our Sun's surface temperature sits at a relatively comfortable 5,500 degrees Celsius. WR 1224. Its surface temperature reaches an absolutely scorching 44,700 Kelvin. That's about 44,400 degrees Celsius, or roughly 80,000 degrees Fahrenheit. At this temperature, almost everything we know would be instantly vaporized. But temperature is only part of the story. WR 124's luminosity, the total amount of energy it pumps out, is approximately 562,000 times greater than our Sun's. Let that sink in for a moment. This single star outputs more energy in 1 second than our Sun produces in nearly a week. It's a cosmic furnace operating at unimaginable intensity. Surrounding WR 124 is a spectacular structure, known as M1267, sometimes called Merrill's Nebula, after the astronomer Paul W. Merrill, who discovered the system in 1938. This isn't just any nebula. It's a graveyard of stellar material, the cast-off outer layers of the star itself. The nebula is approximately 6 light-years across. That's about 60 trillion kilometers, and it's expanding at a rate of over 150,000 kilometers per hour, or about 93,000 miles per hour. Adding to WR 124's mystique is the fact that it's what astronomers call a runaway star. It's racing through the Milky Way at a radial velocity of approximately 200 kilometers per second. That's about 720,000 kilometers per hour, or 447,000 miles per hour. Something in this star's pass, perhaps a supernova explosion of a companion star, or a close gravitational encounter with another massive object, has sent it hurtling through space at this incredible speed. So what exactly is a Wolf-Rayet star? And how did WR 124 get this way? To understand WR 124, we need to understand the Wolf-Rayet phase of stellar evolution. Not every star gets to become a Wolf-Rayet star. In fact, It's one of the most exclusive clubs in the universe. You need to start with a truly massive star, typically at least 20 to 25 solar masses, though WR124 was likely even more massive when it was born. Stars like this begin their lives as what astronomers call U-type or B-type main sequence stars, the most massive and luminous normal stars. These stellar giants burn through their hydrogen fuel at a prodigious rate, living fast and dying young. While our Sun will live for about 10 billion years, these massive stars exhaust their fuel in just a few million years. As these massive stars age, they begin to experience intense mass loss. The radiation pressure from their cores, literally the pressure exerted by the photons of light being produced, becomes so intense that it starts pushing the outer layers of the star away. This isn't a gentle process. We're talking about stellar wind streams of charged particles traveling at velocities of 2,000 to 3,000 kilometers per second. That's roughly 1% of the speed of light. Eventually, these powerful winds strip away the entire hydrogen envelope of the star, exposing the helium-burning core underneath. This is when a star officially becomes a Wolf-Rayet star. The star is now essentially naked, with its nuclear furnace exposed to space. The spectroscopic signature is unmistakable strong emission lines of helium, carbon, nitrogen, and oxygen, elements that would normally be hidden deep within a star. Wolf-Rayet stars are classified into three main types based on their spectra. WN stars show strong nitrogen lines. WC stars show strong carbon lines, and the rare WO stars show strong oxygen lines. WR124 is classified as a WN star, specifically a WN8 subtype, indicating it's still in a relatively early phase of the Wolf-Rayet stage. With its nitrogen-rich layers still partially intact, the mass loss from Wolf-Rayet stars is absolutely staggering. These stars can lose approximately one solar mass every 100,000 to 1 million years. To put this in perspective, our Sun loses about 1/10 of 1/trillionth of its mass per year through solar wind. Wolf-Rayet stars lose material at a rate that's roughly 100 million times faster. The stellar winds from Wolf-Rayet stars are among the most powerful phenomena in astrophysics. These winds can reach velocities of 2,000 to 3,000 kilometers per second. Compare that to our Sun's solar wind, which travels at a relatively leisurely 400 to 750 kilometers per second. The kinetic energy in these winds is absolutely enormous, and they sculpt the surrounding interstellar medium into fantastic shapes. And here's the most important thing to understand about Wolf-Rayet stars like WR124. They're on borrowed time. This phase of stellar evolution is extremely brief, lasting only a few 100,000 years, maybe 1,000,000 years at most. The star is in its death throes, frantically burning through its remaining nuclear fuel. When that fuel runs out, the core will collapse, and the result will be one of the most energetic events in the universe, a supernova explosion. Some Wolf-Rayet stars may even collapse directly into black holes without producing a supernova at all. Now that we understand what WR124 is, let's embark on our thought experiment. What would happen if you somehow found yourself falling toward this stellar monster? To answer this question properly, we need to start your journey from a safe distance and work our way inward, stage by stage, examining each level of hell that awaits. Let's imagine that through some unfortunate series of events, malfunctioning spacecraft, a freak wormhole accident, or perhaps just extremely bad luck, you find yourself on a collision course with WR124, we'll start your journey. We'll start your journey at a distance of 10 light years, or about 95 trillion kilometers. At this distance, WR124 appears as an extraordinarily bright blue-white star, far brighter than any star visible from Earth. Its apparent magnitude would be impressive. perhaps rivaling or exceeding the brightness of Sirius, the brightest star in Earth's night sky. But you're not just seeing the star itself, you're beginning to see the nebula. M1267. The ring nebula surrounding WR124 begins to come into view. From this distance, it appears as a faint, ethereal glow surrounding the central star. The nebula is illuminated by the intense ultraviolet radiation from WR124, causing the gas to fluoresce in characteristic emission lines, the deep red of hydrogen alpha, the blue-green of doubly ionized oxygen, and other colors painting a cosmic masterpiece. But even at this distance, you'd start detecting something disturbing. Radiation. WR124 is pumping out enormous amounts of ultraviolet and X-ray radiation. Your spacecraft's instruments would register increasing levels of high-energy photons. For now, it's manageable, comparable perhaps to the radiation environment near Jupiter, but it's increasing with every kilometer you travel inward. As you continue your approach, closing the distance to perhaps 5 light-years, then 3 light-years, the star grows noticeably brighter. The nebula begins to reveal more structure. It's not a simple sphere, but rather has a knotty, filamentary appearance. These structures are the result of instabilities in the stellar wind, places where the ejected material has clumped together into denser knots and filaments at a distance of approximately 1 light-year, about 9.5 trillion kilometers. You cross an invisible but significant threshold. You enter the outer regions of M1267, the nebula of ejected material surrounding WR124. The view is now spectacular beyond description. You're literally flying through a stellar graveyard, surrounded by glowing gas and dust in all directions. The material here is extremely tenuous. The density is only slightly higher than the near-perfect vacuum of interstellar space, but there's enough of it. You can see it glowing all around you, illuminated by the relentless radiation from the central star. The temperature of the gas in this region is surprisingly varied. In some areas, particularly where the stellar wind is still interacting with older ejected material, shockwaves have heated the gas to temperatures of thousands of degrees Kelvin. In other regions where the gas has had time to cool, temperatures might be merely a few hundred degrees. Mixed in with the gas are dust-grained tiny particles of carbon, silicon, and other heavy elements synthesized in the star's interior and expelled into space. These dust grains are what make Wolf-Rayet stars, like WR124, such important contributors to the chemical evolution of galaxies. They're literally seeding the interstellar medium with the building blocks of future generations of stars, planets, and potentially even life. But the beauty comes with danger. The radiation levels are now becoming serious. The ultraviolet flux from WR124 is intense enough that any unprotected THF, only Ruby Kiss has the luxurious texture that Livy-sized. Any suv, like Suverly Ma, like a love, like Suver sidely come on. My munly kick it, my mully cummers suv, my mully sully camelisis, my Suver's side. It's ESP says. Mave sakade, my ye teed, my mully said, my mully said, my sets. Electronics would begin experiencing problems. Solar panels, if you had any, would actually be a liability. The intense UV radiation would degrade them rapidly. The charged particle density is also increasing. You're starting to feel the effects of the stellar wind. Remember? This isn't just a gentle breeze of solar wind like we experience from our sun. This is a hurricane, a gale, a Category 5 cosmic storm traveling at 2,000 to 3,000 kilometers per second. Even though the density is still very low, the sheer velocity of these particles means they carry enormous kinetic energy. Any spacecraft would need substantial shielding to survive as you continue inward. Passing the 0.5 light-year mark, you begin to see evidence of the episodic nature of WR124's mass loss. The nebula isn't uniform, it shows shells and layers. Like the rings of a tree, each one representing a period of enhanced mass loss. These episodes might be related to instabilities in the star's outer layers, or perhaps to the star transitioning between different stages of nuclear burning. The nebula is expanding at over 150,000 kilometers per hour. At your relative velocity, you're actually overtaking some of this material as you fall deeper toward the star. It's like driving down a highway in the rain. Except the rain is ionized gas moving at a significant fraction of the speed of light at a distance of 0.1 light years, roughly 950 billion kilometers. Or about 20,000 times the distance from Earth to the Sun. Things start getting serious. WR-124 now dominates your view. The star is no longer a point source. It's beginning to show an actual disk, though it's still quite small. But its brightness is overwhelming. The apparent magnitude of WR-124 from this distance is approximately -22, comparable to how bright the Sun appears from Earth's surface. But there's a critical difference. WR-124's light is vastly more energetic. While our Sun's peak emission is in the visible spectrum, a yellow-green light, our eyes evolved to see WR-124's peak emission is in the extreme ultraviolet and even soft X-ray portions of the spectrum. What this means in practical terms is that most of the energy hitting you isn't even visible light, it's deadly high-energy radiation. If you were somehow exposed to this radiation without protection, the effects would be immediate and catastrophic. The UV radiation alone would be strong enough to break apart DNA molecules in seconds. The X-rays would penetrate deep into tissue, ionizing atoms and causing devastating cellular damage. The magnetic field in this region, generated by the stellar wind and the star's own magnetic field, would be intense and chaotic. Recent observations have suggested that some Wolf-Rayet stars possess incredibly powerful magnetic fields, in some cases tens of thousands of Gauss, making them among the most strongly magnetized stars known. If WR-124 has such a field, it would create a complex, dynamic magnetosphere that could accelerate particles to near-relativistic speeds. The stellar wind at this distance is like being hit by a continuous stream of atomic bullets. Each particle, protons, electrons, helium nuclei, and heavier ions is moving at 2,000 to 3,000 kilometers per second. The momentum transfer from these particles would exert significant pressure on any object, trying to push it away from the star. In fact, this brings up an interesting point about your journey. Would you even be able to fall into WR-124? Radiation pressure, the literal push of photons combined with the momentum of the stellar wind, exerts an outward force. For small objects, this force can actually exceed the gravitational pull, making it impossible to approach the star. Calculations show that for dust grains and small particles, the outward radiation pressure from a Wolf-Rayet star like WR-124 is strong enough to blow them away. This is exactly what's happening with the stellar wind. For a human-sized object, though, or certainly for any spacecraft, gravity would still win. You'd continue falling inward, but the radiation pressure would slow your fall slightly. The temperature of any surface facing the star would now be rising rapidly. Even with the best reflective coatings, heat absorption is inevitable. Any spacecraft would need active cooling systems working at maximum capacity. The blackness of space, which usually makes cooling relatively easy through thermal radiation, is now a liability. You're being cooked from one direction with no atmosphere to convect the heat away. At approximately 1 trillion kilometers, still about 7,000 times the distance from Earth to the Sun, or roughly 130 light-years, you enter what we might call the true stellar wind zone. Here, the wind dominates everything. The density of the stellar wind at this distance, while still incredibly tenuous by Earth standards, is orders of magnitude higher than typical interstellar space. You're now in a plasma environment with temperatures in the millions of degrees Kelvin. Yes, you read that right, millions of degrees now. You might be wondering, if the temperature is millions of degrees, why haven't you been vaporized already? This is one of the most common misconceptions about space environments. Temperature and heat are not the same thing. Temperature is a measure of the average kinetic energy of particles. In a plasma, the particles are moving incredibly fast, which translates to high temperature. But heat transfer, the actual heating of an object, depends on density as well as temperature. In the stellar wind, even though individual particles are moving at enormous speeds and have high kinetic energies, there are so few of them per cubic centimeter that the total heat transfer is still manageable, at least for now. It's similar to how you can briefly stick your hand in a hot oven, where the air is hot but not dense, without immediate injury. But you can't put your hand in boiling water where the liquid is hot and dense for even a second. However, the radiation is another story entirely. At this distance, the UV and X-ray flux is now millions of times stronger than what we experience on Earth. Any biological tissue would be suffering catastrophic damage. Even through heavy shielding, the radiation dose would be accumulating. If we could measure it in sieverts, the unit for radiation, those you'd be absorbing lethal doses every minute. The materials of any spacecraft would be degrading rapidly. Polymers would break down, metals would begin to sublimate, ceramics would crack from thermal stress, the stellar wind particles slamming into surfaces at 2,000 kilometers per second would sputter away atoms from any exposed surface, literally sandblasting the spacecraft at the molecular level. If your spacecraft had any magnetic field for protection, perhaps an artificial magnetosphere generator, a concept that's been proposed for real deep space missions, it would be interacting violently with the stellar wind. The field would be compressed on the side facing the star and stretched out into a long magnet tail on the opposite side. Much like Earth's magnetosphere interacts with the solar wind, but far more dramatically, the view would be dominated by overwhelming brightness. WR-124 itself would be far too bright to look at directly, even with the darkest filters. The star would appear as a brilliant blue-white disk surrounded by a vast halo of scattered light. The familiar stars of the background cosmos would be almost completely washed out, rendered invisible by the intense glare at the speeds you'd be achieving in freefall toward WR-124, likely several thousand kilometers per second. By this point, relativistic effects would start to become barely measurable, though not yet significant. Time dilation would be on the order of microseconds per hour real, but not enough to notice without atomic clocks. At approximately 100 billion kilometers, about 670 times the Sun-Earth distance, or about 15 light days, WR-124 appears enormous in your view. The star is now subtending an angle of several degrees across the sky. To give you perspective, the full moon as seen from Earth is only about half a degree across. This star now appears dozens of times larger too. Here we need to discuss an important concept: tidal forces. Gravity decreases with the square of distance, which means the gravitational pull on the side of an object closer to the star is stronger than on the side farther away. This difference in gravitational force across an object is called a tidal force, and it acts to stretch objects along the line connecting them to the star. Every massive body has what's called a roach, limit the distance, inside which tidal forces become strong enough to overcome an object's self-gravity and tear it apart. For rigid objects held together by material strength rather than self-gravity, this limit doesn't strictly apply, but the stresses still increase dramatically as you approach. For WR-124, with its 30 solar masses, the Roche limit for a body with density similar to water, like a human body or many small moons, would be approximately 13 to 15 times the radius of the star itself. WR124's radius is about 12 times larger than our Sun's radius, so roughly 8.3 million kilometers. This means the Roche limit would be somewhere around 100 to 125 million kilometers at 100 billion kilometers. You're still well outside the classical Roche limit. Tidal forces are present, but they're not yet the dominant concern. However, you can feel them beginning to mount. If you were conscious and able to sense such things, you might notice a slight sensation of being stretched. With your head and feet trying to separate from your center of mass, your velocity toward the star is now extraordinary. Starting from effectively zero velocity at a great distance, gravity has accelerated you to speeds approaching 1% of the speed of light, around 3,000 kilometers per second. At this speed, you're covering a distance equivalent to the Earth's diameter every 4 seconds. The radiation environment has now reached levels that would overwhelm any conceivable shielding. The photon pressure is measurable even on large objects. The temperature of any surface directly facing the star, even if made of the most refractory materials known, tungsten, tantalum, carbon composites, would be rising into the thousands of degrees Kelvin. The stellar wind plasma around you is now dense enough that it's beginning to behave more like a fluid than like individual particles. You're essentially moving through a continuous medium of ionized gas. The interaction between this plasma and any solid object creates shock waves, bow shocks, similar to the sonic boom created by a supersonic aircraft, but occurring in plasma rather than air. These shock waves would form in front of any spacecraft, heating the plasma even further. The compressed, shocked plasma would emit intense radiation in its own right, adding to the already overwhelming radiation environment. The physics here are similar to what happens when a spacecraft re-enters Earth's atmosphere at high speed, except far more extreme than any exposed surface would be undergoing. Rapid ablation material being torn away by the combination of intense heat, radiation, and particle bombardment. It would be like the worst re-entry heating ever imagined, except continuous rather than brief. The rate of mass loss would be measured in kilograms per second for any sizable object, at 10 billion kilometers, about 67 times. The Sun-Earth distance you've entered what can only be described as radiation hell. The environment here is so hostile that it challenges our ability to even describe it in familiar terms. The photon flux. The number of photons hitting each square centimeter of surface per second is now astronomical. Most of these photons are high-energy, ultraviolet, and X-rays. The UV flux alone is sufficient to dissociate any molecular bonds on contact. Any organic material would be broken down into individual atoms within milliseconds. The X-rays penetrate deeper, ionizing atoms throughout any material. In biological tissue, though of course no biological tissue could survive here even. For a microsecond the ionization would be total and immediate. Every water molecule would be split, every protein unraveled, every DNA strand shredded into component nucleotides, then into individual bases, then into atomic soup. But it gets worse. At this distance, WR124 is also emitting significant amounts of extreme ultraviolet EUV, and even gamma rays from various nuclear processes in its outer layers. These photons carry so much energy that they can knock electrons completely out of atoms, even from inner electron shells. This creates exotic ionization, states atoms, missing multiple electrons that simply don't exist in normal matter. The effective temperature that a black body at this distance would reach. That is, an object in thermal equilibrium with the radiation environment would be over 10,000 Kelvin. That's hotter than the surface of most normal stars, including our Sun. Any solid matter would be transitioning to liquid, then to gas, then to plasma. Let's think about what this means for actual materials. Iron melts at 1,811 Kelvin. It boils at 3,134 Kelvin. At 10,000 Kelvin, iron exists only as a gas, and that gas is partially ionized to plasma. Tungsten, with the highest melting point of any pure metal at 3,695 Kelvin, fares only slightly better. Carbon, in its graphite form, sublimes at around 3,900 Kelvin under normal pressure. And even in its diamond form, it cannot maintain structural integrity above about 4,000 Kelvin. Some exotic materials, certain carbides, nitrides, and oxide compounds have higher dissociation temperatures, perhaps up to 4,000 or 4,500 Kelvin. But at 10,000 Kelvin, even these break down. There is simply no known material that can exist as a solid or liquid at these temperatures, except perhaps in the fleeting moments before complete vaporization. By this point, anything falling toward WR-124, a spacecraft, an asteroid, a planet, or yes, a human being, has long since ceased to exist in any recognizable form. It has been vaporized, ionized, and broken down into a plasma, hot gas of individual atomic nuclei and free electrons. But here's the fascinating and terrifying thing. Even as plasma, your atoms continue falling inward. The gravitational pull is relentless. The plasma cloud that was once you, now indistinguishable from the stellar wind itself, continues its journey toward the stellar surface. If we had impossibly advanced instruments observing this process from a safe distance, we could actually detect the elements that composed you by their spectral signatures. The hydrogen from your water content, the carbon from your organic molecules, the calcium from your bones, the iron from your blood, all would emit characteristic wavelengths of light as they ionize and recombine, adding briefly to the complex spectrum of WR-127, before being lost in the overwhelming stellar emission at 1 billion kilometers, about 7 times the Sun-Earth distance you're approaching. The outermost layers of WR-124's extended atmosphere, the star's actual photosphere, the visible surface of the stars still several million kilometers away. But the star doesn't have a sharp boundary like a rocky planet. Instead, it transitions gradually from the thin stellar wind to the denser photospheric layers. The density of the plasma is now high enough that it's starting to become optically thick, meaning photons can no longer travel freely. Instead, they scatter off electrons and ions, being absorbed and re-emitted countless times before finally escaping. This is what defines the photosphere. It's the layer where the density becomes high enough that we can't see deeper into the star. The temperature is now climbing rapidly. Not because of external radiation, you're beyond that, nor you're inside the star's extended atmosphere, but because of the local plasma conditions. The temperature in these outer atmospheric layers of WR-124 reaches 25,000 to 50,000 Kelvin, many times hotter than the surface of our Sun. The pressure, too, is climbing. While still far less than atmospheric pressure on Earth, it's now measurable in pascals rather than nanopascals. The plasma density is approximately YY to 1012 particles per cubic centimeter, still far more tenuous than Earth's air at sea level, which has about 1019 molecules per cubic centimeter, but dense enough for collective plasma effects to dominate. The magnetic field in this region is complex and powerful. Wolf-Rayet stars can have magnetic fields of thousands to tens of thousands of Gauss. For comparison, Earth's magnetic field is about 0.5 Gauss, and a typical refrigerator magnet is about 100 Gauss. This intense magnetic field shapes the flow of the stellar wind, channels the plasma, and stores enormous amounts of energy that can be released in stellar flares. And flares are indeed a major hazard here. WR-124, like other Wolf-Rayet stars, experiences violent magnetic reconnection events that release tremendous amounts of energy. These stellar flares dwarf anything our Sun produces. A single flare from WR-124 could release more energy than our Sun produces in an entire month. The radiation, particle acceleration, and magnetic field disturbances from such flares create local conditions even more extreme than the already deadly background environment. The plasma around you is in constant, violent motion. The outer layers of WR-124 are likely convective, with huge cells of plasma rising from below, cooling relatively speaking, and sinking back down. These convection cells are enormous, possibly thousands or millions of kilometers across. The upwelling plasma carries energy from the stellar interior, while the downfalling plasma removes cooler, though still incredibly hot, material from the surface. This is also the region where the stellar wind is actually launched. Radiation pressure from the intense photon flux emerging from deeper in the star pushes on spectral lines particular wavelengths of light, where atoms absorb and remit photons. This radiation pressure accelerates ions outward, and the ions drag electrons with them through electromagnetic forces, creating the wind. The acceleration is enormous. Within a few stellar radii, the wind is accelerated from essentially rest to its terminal velocity of 2,000 to 3,000 kilometers per second. This acceleration, measured in terms of gravitational acceleration, is thousands, or even millions of times stronger than Earth's surface gravity. It's comparable to the acceleration experienced by particles in advanced particle accelerators. The mass loss rate at this distance is staggering. WR-124 is losing mass at a rate of approximately Y-5 solar masses per year. That's about one Earth mass every 30,000 years, or roughly 10,000 kilograms per second. That's equivalent to launching a fully loaded truck into space every single second continuously, for thousands of years, at a distance of approximately 8 to 10 million kilometers from the center of WR-124, about 12 to 15 times the Sun's radius U reach the photosphere, the visible surface of the star. Or rather, what was once U, now a cloud of ionized atoms, reaches it, the photosphere of a Wolf-Rayet. Star like WR-124 is nothing like the relatively calm surface of our Sun. It's a seething, roiling inferno of plasma. The temperature here is approximately 44,700 Kelvin, about 8 times hotter than the Sun's surface. At this temperature, the peak emission is in the ultraviolet spectrum, which is why Wolf-Rayet stars appear blue-white to our eyes. The density in the photosphere is approximately 1015 to YOY particles per cubic centimeter still, millions of times less dense than Earth's atmosphere, but dense enough to behave very much like a gas rather than a diffuse plasma. The composition is exotic, mostly helium, with significant amounts of nitrogen. This is a W1-type star, and trace amounts of carbon, oxygen, and other heavy elements. Notably absent is hydrogen, the most abundant element in the universe and the primary component of most stars. WR-124 has lost almost all of its hydrogen envelope. The surface you're seeing is essentially the exposed interior of what was once a much larger star. You're looking at material that, in a normal star, would be buried under thousands of kilometers of hydrogen-rich layers. The photosphere is defined by opacity. This is the layer where photons from the stellar interior can finally escape into space. Below this layer, photons are continuously absorbed and re-emitted, scattered by electrons and bound up in atomic transitions. Above this layer, photons can travel freely, or at least more freely. The photosphere is essentially where the star becomes transparent. The radiation field in the photosphere is almost incomprehensible. The energy density measured in joules per cubic meters, millions of times greater than an empty space. Every cubic centimeter contains as much electromagnetic energy as a powerful laser beam. This radiation isn't just passing through. It's in thermal equilibrium with the matter, constantly being absorbed and re-emitted. The atoms in the photosphere exist in highly ionized states. Helium, normally with 2 electrons, exists primarily as He-to-helium with 1 electron removed, or even He3 fully ionized helium, just a bare nucleus. Nitrogen exists in ionization states up to N4 or Nv. Carbon and oxygen are similarly stripped of multiple electrons. It's in the photosphere that the characteristic emission lines of Wolf-Rayet stars form. Unlike normal stars, which show absorption lines, dark lines in the spectrum, where cooler atoms absorb specific wavelengths, Wolf-Rayet stars show emission lines, bright lines, where hot atoms emit specific wavelengths. This is because the stellar wind above the photosphere is so hot and luminous that it actually emits more strongly at certain wavelengths than the photosphere itself. The photosphere is turbulent and unstable. Models suggest that Wolf-Rayet stars experience various instabilities, pulsations, convective overturn, and possibly even episodic mass ejections. These events could create local variations in temperature, density, and opacity, leading to the knotty, irregular structure we see in the surrounding nebula. As your atoms for, that's all that remains of you. Now continue their inward journey. They sink below the photosphere into the stellar interior. Here, hidden from the view of any external observer, conditions become even more extreme. The temperature rises rapidly as you descend. Within the first few thousand kilometers below the photosphere, the temperature climbs to 100,000 Kelvin, then 200,000 Kelvin. The pressure, too, increases dramatically. Following the principles of hydrostatic equilibrium, the balance between gravity pulling inward and pressure pushing outward that keeps the star from collapsing. In this region, energy is transported primarily through radiation photons diffusing outward from the hotter interior to the cooler exterior. But diffusing is perhaps too gentle a word. A photon emitted in the core of a star takes thousands or even millions of years to random walk its way to the surface, being absorbed and re-emitted countless trillions of times the mean free path of a photon. The average distance it travels before being absorbed is incredibly short in the stellar interior, perhaps only a few millimeters or even less. This is because the density and opacity are so high. The photon essentially bounces from atom to atom, gradually working its way outward through this maze of matter. The energy flowing through this region is enormous. Recall that WR-124 has a luminosity of 562,000 solar luminosities. All of that energy is being generated in the core and must flow outward through these layers. The energy flux energy per unit area per unit times, millions of times greater than the solar constant we experience at Earth. Deeper still, at distances of perhaps 1 to 3 million kilometers from the center, we encounter the helium-burning regions. WR-124 has exhausted its hydrogen fuel. So the primary nuclear reactions now involve the fusion of helium into heavier elements, primarily carbon and oxygen, through the triple alpha process. In the triple alpha process, 3 helium-4 nuclei alpha particles combine to form carbon-12. This can then capture another helium nucleus to form OXYGEN-16. The energy released per fusion is less than in hydrogen burning, which is one reason why helium-burning stars are so luminous. They have to burn more fuel to maintain the pressure support. Against gravity, the temperature in the helium-burning shell is approximately 200 million Kelvin, 240 times hotter than the Sun's core. The pressure is about 1 billion times Earth's atmospheric pressure. Under these conditions, matter behaves in ways that are difficult to even imagine. It's not quite a plasma, too dense for that, not quite a normal gas, but something in between, partially degenerate electron gas mixed with free atomic nuclei. As you go even deeper, approaching the core, temperatures may reach 500 million to even 1 billion Kelvin in the most extreme regions. Here, heavier elements are being synthesized through successive captures of helium nuclei neon, magnesium, silicon, and others. If the star is advanced enough in its evolution, the very center might even be beginning silicon burning. The final stage of fusion before iron is special in nuclear physics. It's the most stable nucleus, the one with the highest binding energy per nucleon. Fusion of elements lighter than iron releases energy. Fusion of elements heavier than iron requires energy input. This means that once a star's core is largely iron, fusion can no longer provide the pressure support needed to balance gravity. That's when catastrophic core collapse begins, leading to a supernova. We don't know exactly how far along this path WR-124 has traveled. As a WN8 star, it's probably still in the helium-burning phase, perhaps with a small carbon-oxygen core beginning to form. It may be tens of thousands or even hundreds of thousands of years away from its ultimate fate. Or it could be much closer. The final stages of massive star evolution can progress rapidly, with the star running through successive burning stages in years or even days. Finally, your atoms reach the core of WR-124, the heart of the stellar beast. The ultimate furnace where nuclear fire burns at its most intense. The core is surprisingly small, it's only a few 100,000 kilometers across, roughly the size of a large planet or a small star. Yet packed into this relatively tiny volume is several solar masses of matter, primarily helium and the products of helium burning, carbon and oxygen. With traces of heavier elements, the density in the core is enormous, perhaps 106 to 108 grams per cubic centimeter. To put this in perspective, lead has a density of about 11 grams per cubic centimeter. The core of WR-124 is tens of thousands to millions of times denser than lead. A teaspoon of core material would have a mass of hundreds of kilograms to hundreds of metric tons. The temperature at the very center reaches its maximum somewhere between 300 million and possibly even a billion Kelvin, depending on which fusion reactions are occurring. At these temperatures, thermal energies are so high that nuclear reactions proceed at tremendous rates. The star is essentially a self-sustaining thermonuclear explosion, held in check only by gravity. The pressure is almost beyond description, perhaps 1017 to 18 pascals, or about 100 trillion to 1 quadrillion times Earth's atmospheric pressure. Under this pressure, even the electron clouds of atoms are compressed, and matter exists in a partially degenerate state, where quantum mechanical effects become important in normal matter. Electrons orbit atomic nuclei in specific quantum states. The Pauli exclusion principle states that no two identicals fermions particles like electrons can occupy the same quantum state simultaneously. When matter is compressed to extreme densities, electrons are forced into higher and higher energy states because all the lower states are filled. This creates a pressured degeneracy pressure that doesn't depend on temperature, only on density. The nuclear burning rate in the core is prodigious. To maintain WR-124's luminosity of 562,000 solar luminosities, the core must be converting mass into energy at a rate given by Einstein's famous equation, E equals mc. The calculation shows that the star is converting approximately 3 million metric tons of mass into pure energy every second. And most of that conversion is happening right here in this compact core. Nuclear reactions in the core produce not just energy in the form of gamma rays, but also neutrinos, ghostly particles that barely interact with matter, while the gamma ray energy is trapped in the star. Taking thousands of years to diffuse outward, neutrinos escape almost instantly, carrying away a significant fraction of the energy. In fact, for massive stars in advanced burning stages, neutrino losses can exceed photon luminosity. The core is the ultimate driver of the star's fate. As fusion products accumulate, the core's composition changes. Each successive fusion stages hydrogen to helium, helium to carbon-oxygen, carbon to neon-magnesium, and so on operates at higher temperatures, produces less energy per unit mass, and lasts for shorter times. The star is on a countdown to catastrophe. At the extreme densities and temperatures in the core, exotic processes begin to occur. Electron capture, where a proton captures an electron to become a neutron, can begin to turn the core material into more neutron-rich isotopes. Photodisintegration, where high-energy gamma rays have enough energy to break apart atomic nuclei, can reverse the fusion process, consuming energy rather than producing it. When the core finally exhausts its nuclear fuel, when it becomes primarily iron group elements that cannot be fused to release energy, the end comes suddenly. The core loses its pressure support and collapses in less than a second, reaching densities comparable to atomic nuclei. The infalling material rebounds off the incompressible nuclear matter at the center, creating a shock wave that propagates outward. The star explodes as a supernova, one of the most energetic events in the universe. Now that we've completed our terrifying journey from the outer reaches of M167 down to the core of WR124, let's step back and summarize the physics of destruction at each stage. What exactly would happen to a human body or any complex object at each level of this descent into hell? A human body is a complex structure made primarily of water, about 60% by mass, proteins, fats, minerals, and other organic molecules. It's held together by chemical bonds, electromagnetic forces between atoms, and organized into cells, tissues, and organs. Let's trace what happens to this structure as it approaches WR124. Stage 1. The outer. Nebula 1 light-year out at this distance. The primary danger is radiation, mainly ultraviolet and X-rays. An unprotected human would begin experiencing severe radiation burns within minutes. The UV radiation would damage DNA, causing mutations and cell death. Over hours, acute radiation syndrome would develop, with symptoms ranging from nausea to organ failure. Without protection, death would occur within days, but the body would remain largely intact. Stage 2. The inner nebula, 0.1 light-years out here. Radiation levels are lethal within seconds. The UV flux is strong enough to break molecular bonds on the surface of exposed tissue. Skin would begin to char and break down. The water in surface tissues would begin to dissociate, not from heat, but from photochemical reactions driven by UV photons. The body would remain solid for perhaps minutes to hours, but would be receiving truly astronomical radiation doses, with every biological molecule being damaged beyond repair. Stage 3. The stellar. Wind zone, 1 trillion kilometers at this point. We're beyond survivability, even for a brief moment. The radiation alone would deliver fatal doses in microseconds. But now, heat becomes the primary factor. The thermal radiation from WR124 would raise the temperature of a body to hundreds of degrees within seconds. Water would boil away. Organic materials would ignite and burn, even in the near vacuum of space combustion, using oxygen from the decomposing body itself. Within minutes, a human body would be reduced to charred, dried remnants. Stage 4. The extreme radiation zone, 10 billion kilometers here. Vaporization begins. The temperature of any solid object reaches thousands of degrees Kelvin. Organic material doesn't just burn, it sublimes directly from solid to gas, skipping the liquid phase. Minerals in bones might last slightly longer, but not by much. Within seconds to minutes, a human body would be completely vaporized, transformed into a cloud of molecular and atomic gases, water vapor, carbon dioxide, nitrogen oxides, and various organic fragments. Stage 5. Approaching the photosphere, 1 billion kilometers by now. We're dealing with temperatures of tens of thousands of degrees. Molecules cannot survive. The water vapor, carbon dioxide, and other gases from stage 4 are broken down into individual atoms: hydrogen, carbon, nitrogen, calcium, phosphorus, and trace elements. Even these atoms don't retain all their electrons. The UV and X-ray flux, combined with collisions with other hot particles, strips away outer electrons, creating ions Hja, Cja, Oja, Nja, Ki, Jaja, and so on. Stage 6. The photosphere, 10 million kilometers in the photosphere. Even more electrons are stripped away. At temperatures of 44,700 Kelvin, atoms exist in highly ionized states. The cloud of atoms that was once a human is now indistinguishable from the surrounding stellar atmosphere, just another parcel of plasma in the seething stellar surface. The atoms are being buffeted by the violent motions of the stellar wind, accelerated outward to thousands of kilometers per second, only to fall back, caught in the convective currents of the stellar atmosphere. Stage 7. The stellar interior below photosphere. If any atoms manage to sink into the stellar interior rather than being expelled in the wind, they encounter even more extreme conditions. At temperatures of hundreds of thousands to millions of degrees, ionization is complete. Carbon exists as bare C6 plus nuclei, all 6 electrons stripped away. Oxygen is O8 plus. The heavier elements that made up a human body, calcium, iron, phosphorus, exist as bare nuclei surrounded by a sea of free electrons. This is a plasma in its truest form, where matter is completely disassociated into its elementary components. Stage 8. The core center of the star. Finally, in the core, at temperatures of hundreds of millions of degrees and densities millions of times that of water, even the atomic nuclei are no longer safe. At these extreme energies, nuclear reactions can occur. Carbon nuclei might fuse with helium to form oxygen. Oxygen might capture helium to form neon. The very identity of the atoms, the number of protons that defines an element, can change through nuclear transmutation. In a sense, this is the ultimate destruction, not just breaking apart molecules, not just stripping electrons, but actually changing the fundamental nature of the atomic nuclei themselves. To truly appreciate how extreme WR124 is, it's worth comparing the experience of falling into it with falling into other types of stellar objects. Let's run through a few scenarios. Our Sun is a relatively gentle star, as stars go. If you fell toward the Sun, you'd experience lethal radiation at a distance of perhaps a few million kilometers, still well outside the solar corona. You'd be vaporized at a distance of perhaps 100,000 kilometers, well before reaching the photosphere. The Sun's surface temperature of 5,500 Kelvin is actually cool enough that some refractory materials could survive there briefly. The journey would be deadly, certainly, but compared to WR124, it's almost benign. A red supergiant like Betelgeuse is enormous, hundreds of times larger than the Sun but relatively cool, with surface temperatures of only 3,000 to 4,000 Kelvin. You could approach much closer before vaporization. The density in the outer layers is also extremely low, in some cases comparable to a laboratory vacuum. Ironically, you might actually fall through the outer layers of a red supergiant and only experience critical heating deep in the interior. Of course, you'd still die, but the mechanism would be quite different from WR124, a blue supergiant, which is what WR124 was before it lost its envelope. Is more similar to WR124 in terms of temperature and radiation output, though generally less extreme. The experience would be similar, but somewhat less intense, like comparing being burned in a regular fire versus being burned in a white-hot chemical fire. Now we're talking about a different league entirely. A neutron star is far smaller than WR124 only, about 20 kilometers in diameter, but its gravity is so intense that you'd be accelerated to a significant fraction of the speed of light during your fall. Tidal forces would tear you apart long before you reach the surface. If somehow your atoms made it to the surface, they'd impact at perhaps 50% of the speed of light, with kinetic energies high enough to cause nuclear reactions. The entire mass of a human body converted to energy by this collision would release an explosion comparable to hundreds of nuclear bombs. A stellar mass black hole would subject you to tidal forces that would stretch you into a stream of atoms long before you reached the event horizon, the process colorfully termed spaghettification. 4. A supermassive black hole. Interestingly, the tidal forces at the event horizon are much weaker because the horizon is so much farther from the singularity, and you might actually survive crossing it, only to be destroyed closer to the singularity. Either way, the physics inside a black hole is so exotic, involving severe spacetime, curvature, and possible singularities that it's in a category of its own. WR-124 occupies a unique position in this hierarchy of destruction. It's not as gravitationally extreme as a neutron star or black hole, but its combination of intense radiation, extreme temperature, and violent stellar wind makes it one of the most immediately hostile environments in the universe. The sheer rate of energy output per unit area, the intensity of the assault on any matter that dares approach is nearly unmatched except by the most extreme objects like magnetars or the accretion disks around black holes. While the thought experiment of falling into WR-124 is certainly terrifying, it's worth stepping back from the horror and appreciating why astronomers are so fascinated by Wolf-Rayet stars. These stellar monsters, for all their violence, play crucial roles in the cosmos and help us understand some of the most fundamental questions in astrophysics. Cosmic chemical factories. Wolf-Rayet stars are among the most important producers of heavy elements in the universe. Through their nuclear burning, they create carbon, oxygen, neon, magnesium, silicon, and heavier elements up to iron. But unlike most stars, which keep these elements locked away in their cores until death, Wolf-Rayet stars are actively ejecting this enriched material through their powerful winds. The nebula M1-67 around WR-124 contains significant amounts of carbon, nitrogen, and oxygen elements that are essential for life as we know it. The carbon in your body, the oxygen you breathe, the nitrogen in your DNA, much of this may have originated in Wolf-Rayet stars billions of years ago. When WR-124 eventually explodes as a supernova, it will scatter these elements across interstellar space, where they can be incorporated into new generations of stars and planets. Dust producers. Recent observations by the James Webb Space Telescope and other instruments have revealed that Wolf-Rayet stars are prolific dust producers. The carbon-rich material in their winds can condense into dust grain-stainy particles of graphite, silicon carbide, and other compounds. These dust grains are important for several reasons. First, dust grains are essential for star formation. In molecular clouds, dust provides surfaces where molecules can form and helps cool the gas, allowing it to collapse under gravity to form new stars. Second, dust grains are necessary for planet formation. They're literally the seeds from which planets grow. Third, in carbon-rich dust, you find organic molecules, polycyclic aromatic hydrocarbons, PAs, and others that might be prebiotic molecules, chemical precursors to life. Supernova progenitors. Wolf-Rayet stars are among the most likely progenitors of type Ib and type Ic supernova that show no hydrogen in their spectra because the progenitor star has lost its hydrogen envelope. By studying Wolf-Rayet stars, we can understand what conditions lead to different types of supernova and possibly predict which stars might explode, some Wolf-Rayet stars particularly. The most massive ones with rapid Rotation may even be progenitors of long duration. Gamma ray bursts, GRBs. The most energetic explosions in the universe since the Big Bang. Understanding the connection between stellar properties and these extreme events is a major goal of modern astrophysics. Testing stellar evolution theory. Massive star evolution is complex. It involves nuclear physics, hydrodynamics, magnetic fields, rotation, and mass loss all coupled together in intricate ways. Wolf-Rayet stars provide crucial tests of our theoretical models. By comparing observations of real Wolf-Rayet stars, their temperatures, luminosities, mass loss rates, wind velocities, and chemical compositions with theoretical predictions, we can refine our understanding of how massive stars live and die. Galactic evolution on larger scales. Wolf-Rayet stars and their eventual supernova have profound effects on galaxy evolution. Their stellar winds and supernova explosions inject energy and momentum into the interstellar medium, driving galactic winds that can regulate star formation. Their ionizing radiation creates H2. Regions bubbles of ionized hydrogen that can trigger or suppress star formation in surrounding molecular clouds. The heavy elements they produce enrich the interstellar medium, gradually increasing the metallicity of galaxies over cosmic time. Recent discoveries: the James Webb Space Telescope's observations of WR-124 and its nebula M1267, released in March 2023, revealed unprecedented details of the dust, distribution, and structure in the nebula. The images show that the nebula is far more complex than previously thought, with knotty structures, shells, and filaments that suggest episodic mass loss rather than a steady wind. These observations are helping refine models of mass loss in Wolf-Rayet stars. So, what does the future hold for WR-124? We've explored what would happen if you fell into it now. But the star itself is on a journey, a countdown to one of the most spectacular events in the universe currently. WR-124 is in its Wolf-Rayet phase, actively burning helium in its core and possibly carbon in inner shells. Based on its classification as a WN8 star, it's probably in an earlier stage of Wolf-Rayet evolution, with significant nitrogen still present in its winds from the CNO processed material of its former hydrogen envelope. Astronomers estimate that WR-124 has perhaps tens of thousands to a few 100,000 years remaining in its life. In cosmic terms, this is the blink of an eye. The star is 8.6 million years old, quite young compared to our 4.6 billion-year-old Sun, but for such a massive star, this is actually fairly advanced in its lifetime. Over the coming millennia, WR-124 will continue fusing helium into carbon and oxygen in its core. The carbon-oxygen core will grow in mass as more helium is converted. Eventually, the helium in the core will be exhausted, and the core will begin to contract under its own gravity, heating up until carbon fusion can ignite. Carbon fusion produces neon and magnesium. When carbon is exhausted, the core contracts further, and neon burning begins, producing oxygen and magnesium. Then oxygen burning, producing silicon and sulfur. Finally, silicon burning, producing iron group elements. Each successive stage operates at higher temperatures, burns faster, and produces less energy per unit mass. The timeline of these final stages is dramatic. Carbon burning might last for thousands of years. Neon burning lasts only about a year. Oxygen burning lasts only months. Silicon burning, the final stage before iron, lasts only days. Once the core is primarily iron, the star has run out of nuclear fuel. Iron fusion doesn't release energy. It requires energy input. At this point, the core has no source of pressure support to balance gravity. It collapses catastrophically in less than a second, falling from the size of a small planet to the size of a city about 20 to 30 kilometers in diameter, about a quarter of a second. The density reaches nuclear densities approximately 1,017 kilograms per cubic meter, similar to the density inside an atomic nucleus. The infalling material encounters the incompressible nuclear matter at the center and bounces back, creating a shock wave that propagates outward through the star. The energy released is enormous, about YY joules, or 100 foes. 1 foe equals 1,044 joules, the standard unit for supernova energy. For comparison, this is approximately 100 times the total energy our Sun will produce in its entire 10 billion year lifetime. Released in a few seconds, the shock wave blows the star apart in a Type Ib or IC supernova. Type Ib if some helium remains. Type IC if even the helium has been stripped away. For a few weeks, the supernova will outshine all the other stars in its galaxy combined. The expanding debris, enriched with heavy elements, synthesized both during the star's life and in the supernova explosion itself, will slam into the existing nebula M1267, creating an even more spectacular structure. Over thousands of years, the supernova remnant will expand, cool, and gradually mix with the interstellar medium. The elements forged in WR124's core and in the supernova explosion: carbon, oxygen, silicon, iron, and even heavier elements, like gold and platinum created in our process during the explosion, will be recycled into future generations of stars. What remains at the center depends on the exact mass of the core at the moment of collapse. If the core mass is below about 2 to 3 solar masses, it will settle into a neutron star, incredibly dense object where protons and electrons have been squeezed together to form neutrons. If the core mass exceeds this limit, even neutron degeneracy pressure cannot support it, and it will collapse further into a black hole to possible futures. Given WR124's current mass of about 2 solar masses and its history of mass loss, the final core mass is difficult to predict precisely, but it's likely in the range where either outcome is possible. The star might leave behind a neutron star, perhaps a pulsar if it has significant spin, or it might collapse directly into a stellar mass black hole of perhaps 5 to 15 solar masses. Regardless of which outcome occurs, the impact of WR124's death will ripple across the galaxy. The elements it has produced will enrich the interstellar medium in its region of the Milky Way. The energy of the supernova might trigger new star formation in nearby molecular clouds, or might disperse clouds and suppress star formation. The compact remnant neutron star or black hole might receive a kick from asymmetries in the supernova explosion, sending it racing through the galaxy at hundreds of kilometers per second, just as WR124 itself is doing now as we near the end of our journey. It's worth taking a moment to reflect on what this thought experiment tells us about the universe and our place in it. We live on a small planet orbiting an ordinary star in an unremarkable region of a typical spiral galaxy. Our existence is predicated on conditions of astonishing gentleness: liquid water, moderate temperatures, a protective atmosphere, a stable sun. We evolved in and are adapted to an environment that, cosmically speaking, is extraordinarily rare and fragile. The universe, however, is not gentle. It's a place of extremes that dwarf human imagination. The interior of WR124, with its temperatures of millions of degrees and densities millions of times that of water, represents conditions that are commonplace in stellar cores throughout the universe. Billions of stars are undergoing similar processes right now. The message is humbling. Humans, and indeed all life as we know it, can only exist in the tiniest fraction of cosmic environments. We require a narrow range of temperatures, pressures, and radiation levels. Step outside these bounds, and our molecular machines break down. Venture into the 99.99999 percent of the universe that isn't a habitable planet's surface. And death is swift and certain. And yet, there's another perspective. Life exists at all because of stars like Milky Way 124. Every atom heavier than hydrogen and helium in your body, the carbon, oxygen, nitrogen, calcium, iron, and dozens of trace elements was forged in the cores of massive stars and scattered into space when those stars died. In a very real sense, we are made of stardust. The universe's hostility is what created us, the violence of stellar winds, the infernos of stellar cores, the cataclysm of supernova. These aren't just destructive forces. They're creative forces. They create the heavy elements, disperse them through space, compress molecular clouds to trigger star formation, and ultimately provide the raw materials from which planets, atmospheres, oceans, and life can emerge. Looking forward, one might wonder, could advanced civilizations ever harness or survive near such extreme environments? Could megastructures survive in the vicinity of a Wolf-Rayet star, perhaps harvesting its prodigious energy output? The physics seems to say no. The radiation and particle flux would overwhelm any conceivable material. But perhaps with technologies we can't yet imagine, with materials and energy sources beyond our current understanding, even these infernos might one day be approached. For now, we can only study such objects from afar, using telescopes to analyze their light and infer their properties. The thought experiment of falling into WR-124 is just that, a thought experiment, a way of understanding the physics, a tool for grasping the truly alien nature of these cosmic beasts. But what a thought experiment it is! From the ghostly beauty of the nebula to the nuclear inferno of the core. WR-124 represents extremes that expand our conception of what's possible in nature. It reminds us that the universe operates on scales and under conditions that evolution never prepared us to intuitively understand. So, to answer our original question, what if you fell into WR-124? The answer, as we've seen, depends on where exactly you mean. Fall into the nebula M1267, and you'd die from radiation poisoning within days, and pleasant, but relatively slow by cosmic standards. Fall deeper into the inner stellar wind region, and you'd be vaporized in minutes. Approach the photosphere, and you'd be broken down into individual atoms in seconds. Reach the stellar interior, and you'd be ionized into plasma instantly. Make it to the core, and your very atomic nuclei might be transmuted into different elements through nuclear reactions. In every case, the outcome is the same: complete and utter destruction. Not just death, but obliteration at the molecular, atomic, and possibly even nuclear level. There would be no remains, no trace, nothing left to indicate that you had ever existed as a complex, organized structure. You would become one with the star, your atoms absorbed into its plasma, perhaps eventually expelled in the stellar wind, or perhaps locked away until the star's death in a supernova. It's worth noting that this isn't even the most extreme fate possible in the universe. Black holes, magnetars, and the collision of neutron stars present scenarios that are in many ways even more destructive. But WR-124 occupies a special place. It's massive enough, hot enough, and violent enough to be truly deadly. Yet it's still a star, an object we can observe, characterize, and to some degree understand using known physics. The 2023 images from the James Webb Space Telescope gave us our best view yet of WR-124 and its magnificent nebula. These observations showed details never before seen: the intricate structure of the nebula, the distribution of dust, the complex interplay between the stellar wind and the ejected material. They remind us that even as we contemplate the destruction such an object would wreak on human scales, on cosmic scales, it's a beautiful and scientifically invaluable laboratory. Future observations, perhaps with even more advanced telescopes, or with spectroscopic instruments that can analyze the wind composition in detail. We'll continue to refine our understanding of Wolf-Rayet stars. Each new piece of data helps us understand massive star evolution, supernova progenitors, and the chemical enrichment of galaxies. WR-124 is just one of hundreds of known Wolf-Rayet stars in our galaxy. And there are surely thousands or millions more in galaxies throughout the universe. Each is a stellar titan, burning brilliantly, living fast, and dying young. Each is enriching its surroundings with heavy elements. Each will, in time, explode and scatter its contents across space. And each, if you were somehow to fall into it, would destroy you so completely and so swiftly that it almost transcends the concept of death as we understand it. It would be transformation, transmutation, a conversion from organized complexity to elementary simplicity. You would become light, heat, plasma, and eventually, stardust once again. Thank you for joining us on this terrifying journey into WR-124. I hope it's given you a new appreciation for both the extremes of the universe and the remarkable gentleness of the small corner we call home. If you enjoyed this cosmic thought experiment, please give this video a thumbs up and subscribe to the Cosmic Atlas for more explorations of the universe's wonders and terrors. Hit that notification bell so you don't miss our next journey into the cosmos. This content is made possible by viewers like you. If you'd like to support the channel and help us create more in-depth astronomical content, check out our Patreon link in the description. Your support helps us invest in better research, visualizations, and production quality. What cosmic object should we explore next? Should we venture into a neutron star, fall into a supermassive black hole, or perhaps visit the surface of a magnetar? Let us know in the comments below. We love hearing your suggestions and your thoughts about these videos. And if you want more extreme space environments, check out our videos on what if you fell into Jupiter, and what if you stood on the surface of the Sun. Links in the cards above and in the description. Connect with the Cosmic Atlas on Twitter and Instagram. We share fascinating space facts, behind-the-scenes content, and updates on upcoming videos. You can find our handles in the description for those wanting to dive deeper into Wolf-Rayet stars and stellar evolution. We've compiled a list of scientific papers, articles, and educational resources in the description. We always strive to be scientifically accurate while making complex topics accessible. And we want to provide pathways for those of you who want to explore further. I'm your host at the Cosmic Atlas, reminding you to keep looking up. Keep asking questions and never stop exploring. The universe is vast, mysterious, and often dangerous, but it's also the most magnificent story ever told. And we're privileged to be part of it, even from our small, safe, beautiful planet. Until next time, stay curious, explorers. The cosmos awaits.